Can you see the screen, please? Can you check if you can see the screen?
Yes, the screen is visible.
Can you see my presentation?
Yes, sir.
Hello, I guess live stream started.
Yeah, I think Deepika can start us off.
Hello. Hello.
Yes, you're audible.
Yeah, you're audible, Deepika.
Okay.
All brand.
So should I start, Sirish?
No, sir. Actually, Deepika will introduce us first, and then Ranjit sir will speak briefly, and then you can start, sir.
Should I start?
Hello, sir. Am I audible?
Oh, I forgot to turn on the my speaker. So okay, so I was not able to hear you. So now I am. I'm sorry,
Okay.
I forgot to turn on the speaker. Yeah.
Sir, Deepika will be starting, then Ranjit sir will speak, and then you can start, sir.
Okay, fine.
Deepika, you can start now.
Paul Brandt once sung, "Don't tell me the sky's limit when there's footprints on the moon." In his famous song, "There's a world out there." A warm and cheerful morning to everyone. I'm Deepika from IITDM Kannur. Welcome to today's webinar. Today, we have Professor Arun Mangalam with us to talk about 2020 Nobel laureates in physics and their discoveries in the field of black holes. I request Dr. Ranjit sir to introduce the speaker.
Thank you, Deepika. So, good morning, everyone. I'll give a brief introduction of today's speaker, Professor Arun Mangalam. He's taken his BTech from Indian Institute of Bombay in 1985. After he has pursued his PhD from Georgia State University on physics and astronomy. Further, he has been working as a research associate in University of Illinois at Urbana-Champaign. Further, as a postdoc fellow at Inter-University Center for Astronomy and Astrophysics, Pune, Maharashtra. For the last 2 decades, he has been working as professor at Indian Institute of Astrophysics, Bangalore. Professor Arun Mangalam is currently working professor and lecturer of theory group at Indian Institute of Astrophysics, Bangalore. He does research in theoretical astrophysics, gravitational dynamics, relativistic astrophysics, gas dynamics, and magnetic fields. His interests include relativistic, high-energy, stellar, dynamical, and hydromagnetic processes concerning black hole systems, galaxies, cosmology, and solar plasma. He also teaches undergraduate and graduate physics and astrophysics courses. Currently, he is working on a project on relativistic, magnetic, and dynamical astrophysics. I welcome you, sir. Sir, over to you.
Okay, so I'm going to start. I think there was a slight delay maybe while coming in, so I apologize. So this year's Nobel Prize was awarded to 3 people, and I'll just go through the overview of the talk here. I'll describe the citation of the prize and the winners, a brief history of black holes, and the black hole paradigm, the foundation, the theoretical foundation for its existence, and the interior of black holes, and the extent and the exterior, which is the part 2 of the citation of the prize, and its implication, and I'll discuss the modern trends. I've not been informed about the time, but I assume that I have about 1 hour or something. Is that correct?
Yes, sir. You have 1 hour.
Okay, thank you. Now, these are the winners. On the left is Roger Penrose. Then you have Reinhard Genzel. Roger Penrose is from University of Oxford. and he got half the prize, which is for black hole formation being a robust prediction of the general theory of relativity. The other half was jointly shared between Reinhard Genzel from Max Planck Institute for Extraterrestrial Physics in Germany, and then the it was shared. So this next quarter, so it is half, quarter, and quarter of the prize was shared with Andrea Ghez of UCLA, USA, and the latter two they were awarded for the discovery of the supermassive compact object at the center of our galaxy, which is thought to be a black hole. The total prize money was 10 million kroner, Swedish kroner, which was, of course, a legacy of the king, and that was also contributed partly by Nobel. And this money was invested, and the interest from that money is given as prizes every year in several disciplines. So this amounts to about 8.3 crores. So 8.3 crore rupees. And so you can see that Penrose got about 4 crores and the other two got 2 crores each, which is not much. You probably can't get a plot in an area like Kormangla for this money. In any case, um, moving on, Roger Penrose, one of the winners, is basically an English mathematical physicist. He's a mathematician, philosopher of science, and Nobel laureate. He's right now, and he's been, of course, he's an FRS and Order of Merit, given the Order of Merit, which is an important recognition in UK, and he's largely been working in the area of mathematical physics. He's also thought about issues in like consciousness, worked in computer science, and so he's a very he's got a diverse interest, and he's always been engaging with the public. So he's very well known public figure even before he got the prize, and getting the prize only makes a very small uh, change to his public persona and people and his celebrity status. He's also written uh, popular publications on various topics, which is very interesting books, and certainly young people should read them. And where he shows his fertile imagination in many things, including consciousness, cosmology, um, limitations of computers, etc., etc. And he's written a lot of technical books, differential topology. He started out doing topology in his early career as a mathematician, and he's worked on spinors and space-time. The two volumes, spinors and twistor methods, are very important contributions to the subject. Reinhard Genzel uh, is another astronomer. By the way, I've kept the chat box on, so in case somebody wants to jump in with a question, you can uh, put the question in the chat box. I might take a look at it from time to time. Okay,
Okay, sir.
so yeah, so Reinhard Genzel is a German who's now the director of the Max Planck Institute, and he's also a emeritus professor at University of California, Berkeley. His research interests are very wide in astrophysics, includes galactic nuclei, ultraluminous infrared galaxies, QSOs, that is quasi-stellar objects, active galactic nuclei. I assume this is an astronomy club, so there are some people who know what they mean, right? And he's also worked on stars and planets. Um, he's been he worked His early career was at Harvard Smithsonian Center for Astrophysics in Cambridge, uh, and he was a full professor at Department of Physics at University of California from 1981. Um, so uh, obviously, he's not as senior as Penrose, who was born in 1931. I think 31 was the yeah, and so you can see that Penrose is quite senior, whereas Genzel was born 1952, so he's pushing 70 now, roughly, and he's lectured at various places in Munich, etc., and he's a full professor at University of California. Andrea Ghez is a is the youngest amongst them. She was born in 1965, and she's pushing 65 now, and is probably you know still continuing her research in full blast. All of them are still doing some research, and she's originally a New Yorker, but moved to Chicago, and she attended the Chicago Lab School, and she was inspired by the Apollo moon landings, and she wanted to be a female astronaut. And by that time, she was already majoring in mathematics, and then she changed to physics, in which she did from MIT in '87, and and finally did a PhD at Caltech in California. I mean, at Caltech in 1992. She's been essentially focusing on the center of the Milky Way galaxy, and this has been a large part of her research. Now, there have been several Nobel Prizes awarded to the field of astrophysics, starting from Hans Bethe in 1967, who got the prize for um, discovering the energy production in stars. So, for example, the sun is putting out its energy, and what is the source of its energy? It's actually nuclear reactions which are happening at the center. Uh, some people who are familiar with astronomy would tell you that there are different chains of nuclear reactions which happen at the center, primarily proton-proton reaction to produce helium is happening at the center, and then a little bit of the CNO cycle is also happening. So he was, he discovered it, and later on in 1974, Martin Ryle and Anthony Hewish discovered pulsars, and both were, and they were also given the prize for making progress in radio astronomy. In 1978, marked the you know the recognition for the discovery of cosmic microwave background radiation, which is the relic radiation from the Big Bang, and was given to Penzias and Wilson, who are basically engineers, but they found that the very sensitive microwave detector was picking up some noise, and this noise turned out to be the cosmic microwave background radiation. And then Chandrasekhar and Fowler got it for white dwarf theory and stellar nucleosynthesis, respectively. Then Hulse Taylor for the discovery of the double pulsar. And in 2002, it was shared between the neutrino astronomy and X-ray astronomy. And in 2006, again, it went to the black body form, but this time it was for the anisotropy in the black body radiation. And it was shared between John Mather and George Smoot. Um, and you might know, I think there's a mistake I forgot to add. This Brian Schmidt Perlmutter is also supposed to be credited for this. So his name is missing here. I apologize. So Schmidt, Perlmutter, and Rice for the discovery of accelerating expansion. So it was found that at least we think today that the universe is expanding. There are some speculation and doubts about it, but uh, so far it seems to hold that we are in an expanding universe. And more recently, Kip Thorne, Barry Barish, and Rainer Weiss they got the prize for detection of gravitational waves. And last year's prize also went to astronomy, a combination of large scale structure in the universe and also for the discovery of exoplanets. And for this year, as I mentioned, it was given for the prediction of general relativity and discovery of the black hole at the center of our galaxies. Now, moving on to the subject itself, black holes, uh, there are many kinds of black holes. Black holes are at the stellar mass scales, which mean that they're of the order of uh, few stellar mass or 8 to 10 stellar mass. And so these kind of black holes uh, are found in several places in the galaxy. And there's also a supermassive black hole at centers of galaxies. And these galaxies are massive. They start from million solar masses to higher than that. And so they are lurking at the centers of galaxies. And what it is a black hole is a region that cannot communicate with the rest of the universe. It's a singularity in Einstein's equation. And it also has a major property important property that charge, angular momentum, and mass are. Okay. Any questions so far? No, okay. So charge, angular momentum, and mass, they specify the black hole. The brief history of the idea. If you try to find escape velocity from a mass, you'll get, half half mv squared equals gm by r, and then if you solve that, you get, for the speed of light, you'll get a radius 2 gm by c squared. So this is called the Schwarzschild radius, but it was found from Newtonian mechanics, and it's a very strange thing, which Einstein found the general relativistic theory in 1915, and since then there have been various solutions which have been found out immediately. Carl Schwarzschild wrote the spherically symmetric solution for a point mass, and Chandrasekhar pointed out in 1931 there's a maximum mass limit for degenerate stars, and if you can simply estimate it by comparing the Fermi energy with the gravitational energy of the star, and by comparing them, you will get the an estimate of the number of baryons that are there in the system, and that turns out to be 2 times 10 to the power 57. So the maximum, so you multiply that by the baryon mass, which is typically let's say the proton mass, you'll get 1.5 solar masses, which is a very good estimate of the a maximum mass of the white dwarf. Moving on, this is the first metric that was discussed. As I said, Schwarzschild found it in 1916. And what is a metric in general relativity? It tells you the structure of space-time. So on the left you have ds squared. So if you're trying to make any measurements in the metric, if there is a dt and the dr squared and the d theta squared, so it's spherically symmetric. And for photons, this ds squared is exactly 0. But for particles, you will have a time-like or a space-like separation for events, right? So if you look at this metric, there are two intriguing features. If you put r equal to 0, it blows up, or one of the terms will vanish. So if you put r equals 2m, again, one of the terms vanishes, that is the metric coefficient will vanish, and the other term will diverge. So what is the significance of this metric? This was what is the meaning of this divergence that is found? So researchers found out that r equal to 0 was a true singularity, and r equal to 2m can be transformed away by a choice of coordinates. So from this spherically symmetric system, you can calculate the escape velocity from general relativity for a static observer. Suppose you have an observer sitting at a distance r from the center, and you can calculate the energy, and from the energy you can find out the speed that is required to leave the system. So let's say that is gamma m. So by doing this calculation, forget about the metric coefficients, which you can see is GTT is, by the way, the coefficient of t, that is dt squared, that is 1 minus 2m by r. You can see that here. And so that is required in the calculation. And then you find out that the observer's proper velocity. And so if you don't know GR, you can, all you can see is this, what's most relevant is that the energy, when it is found out in GR and equated to gamma m, which is the local energy, gamma mc squared would be the local energy. C is equal to 1 in this calculation. And you will find that V is square root of 2m by r, which is exactly what was proposed by Laplace and Michel. So it's a value that's very coincident, that it is the same in GR as well as in Newtonian mechanics. The other thing you can see is that the clock at infinity is faster than the local clock. So what do I mean by it? If you take the d tau squared, which is there on the second equation, and if I go to infinity, you see that d tau squared is dt squared. And if you compare that with a point, let's say at r equal to r, so there you will see that just 2m by r, it's the dt squared will be, because it's 1 by 2m by r, it is going to be, if you compare the two, it is the clock at infinity is running faster than the local clock. All right, because if this is equated, the proper time will be equated. You will get both equated at r equal to 0 and infinity. You will find that not r equal to 0, at r equal to some finite point, you'll find that the clock at infinity is faster than the local clock, let's say in front of the black hole. This leads to a very interesting result that if you take a photon that's emitted very close to the black hole, around the black hole, and the radius of emission is REM, then the frequency would change, right? The frequency would become lower of the photon as it goes out. So suppose you have an X-ray photon that's released, or a gamma ray photon, it becomes UV, and then optical, radio, etc. as it gets out. Another useful metric is the Kerr geometry. The Kerr geometry is for a spinning black hole. So here is a system where I'm talking about a non-spinning black hole, the Schwarzschild metric. So in this case, it's a case of a rotating black hole. So the rotating black hole has this unique feature that you have the metric that is 2m by r by rho squared, where rho squared is r squared plus a squared cos theta. These are called Boyer-Lindquist coordinates. And it's a very special metric which was derived by Kerr. So you can do orbits in Kerr geometry. You can calculate motion of particles around the black hole or stars around the black hole. You can find out the effective potential. You must have done in classical mechanics or mechanics two-body problem. But here you have a rotating black hole, so the potential is more complicated. And you can also find an innermost stable orbit, circular orbit around the black hole. And this is very important. So once you find this radius of which you can find out by taking the potential at a particular radius, equating the potential to solving this energy equation to find the value at that particular point, and then the derivative in first derivative of the potential is set to 0, and the second derivative is also set to 0. So this gives you three conditions, right? So once you solve for it, you'll find the ISCO radius, and this is how the radius behaves from a counter-rotating black hole to a black hole that is co-rotating. So in other words, if a particle is going against the spin of the black hole or counter to the spin of the black hole, the radius will change. and 1 minus e is the amount of energy that can be radiated by the particle, for a particle that's coming in from infinity. So if you calculate the amount of energy that can be radiated, uh, you can see that the radiation can vary from about 4%, 0.0377, so 3.7%, 3.8%, and it becomes 6% for a non-rotating black hole, so 0.0572, and then about 43% for a rapidly rotating black hole. So, uh, as engineers, you know that efficiency of any system it's very difficult to uh, enhance the efficiency of, for example, solar heating or uh, the steam engine, the locomotive, uh, petrol-driven cars, chemical energy conversion. So these are all very difficult places to increase the efficiency. But black holes are the most efficient. You can see that you get 43% of its rest mass energy that can get converted to radiation. So that's a huge amount of efficiency that can be extracted from these systems. And if you look at orbits in Kerr geometry, you'll have to look at several important radii. One is the horizon. That is the point at which the light cannot, even the light is trapped from within the horizon. There is a stationarity curve. If you enter the stationarity region, you cannot survive. I mean, you have to fall into the black hole. So no observer can get inside the stationarity curve. And then there is you can orbit uh, under the black hole's gravity in non-circular terms in region 3, and then
Live streaming is on.
okay,
Sorry about that. You can continue.
fine. So these are the different kinds of regimes, dynamical regimes around the black hole, and you can see that with an effective potential, this line that you see at the top, it describes the circular orbit, and at the bottom, wherever it's sort of tangent to the blue line, you'll get circular orbits, or you'll get orbits which are just elliptical orbits, for example, in the top right, or you can get a stable circular orbit on the left, top left. So you have a stable circular orbit, an elliptical orbit on the right, and then one. In region 2, you have a what is called the separatrix orbit, and this is at the innermost stable bound orbit, which you see in the last figure. What it means is that unlike this is a case of a non-circular bound orbit, so you can see an ellipse, but the ellipse is sort of precessing around the black hole. So it describes a rosette pattern. So you can see the ellipse itself is rotating around the black hole, and this is called the periastron precession. So the ellipse is sort of precessing around the black hole, and this happens only in Schwarzschild geometry. It doesn't happen in Newtonian gravity. So, having seen these interesting features of orbits, there's another interesting feature called the ergosphere. So, moment you have a rotating black hole, this ergosphere comes into play, and if you have the event horizon and the last uh, and the surface of stationarity where an observer can exist without falling into the black hole, so those two radii are the same when the spin is 0. But if the spin is increased to zero point 0.5, that they separate out, right? And you will see that there are two radii which appear, r plus and r minus, and you can see that there's re, which is the radius of the ergosphere, which is separated out. So you can look at the radii at different, different spins, and finally, when there is an R minus and R plus both merge where for A equal to 1, but you can see that the ergosphere has a certain different shape at the end. And this is in that was in the coordinates, Boyer-Lundquist coordinates, in actual radial coordinates, this is how it looks. All right. So the next figure is about the black hole landscape. So this contains the many topics that are being discussed in the literature and also are important topics for sort of hot topics in the field of black holes. In the interior region of black holes, which is now marked in a different color, in a sort of a green color, light green color, you see this. There are essentially, this is a regime of black hole mathematics. So you have singularity theorems, black hole entropy, quasi-normal modes, the cosmic censorship hypothesis, which we will now. So this singularity theorem is where Roger Penrose made an important contribution, and subsequent to that, and also it was shared with the Nobel Prize was shared for discovering orbits around black holes and then finding the mass of the black hole of our Milky Way. And in 2017, the prize went to for the discovery of gravitational waves. So the black hole idea already has bagged 3 prizes, and there are several other ideas which are very important in the progress of the theory of general relativity and also in understanding astrophysical phenomena. So I've just listed out the various different problems, and you can see that 3 Nobel Prizes have already been awarded in this area of research. This is a snapshot of the concept which got the prize for Penrose. So he came up with this idea in 1965. So when there is a massive star which collapses, right, and when the star collapses, it has a certain horizon, 2 gm by r. So when the collapse scale becomes smaller than 2 gm by c squared, its own event horizon. So when the matter gets inside the event horizon, it cannot stop itself. It collapses to a single point and singularity. So this proof of this was why Roger Penrose got the prize. On the right of this, you will see the same idea. You see a light cone. Light cone has got a forward part and a backward part. So the yellow part is the forward part. That's where the photons can go out in the future. And the white part of the light cone is where the photons are entering. So there's a future and the past of the light cones. And you can see that the light cones, once it hits the event horizon, it sort of tilts towards the singularity. So which means that all the light rays are going inside. So you can never see light rays or the particles once they enter the event horizon, they cannot be observed by an external person, right? So an external observer cannot watch this event beyond a point. Once it enters the event horizon, the matter enters the event horizon, then it cannot be observed. So that's the basic reason for this. And the prize was given to explain how this actually happens. Prior to the idea by Penrose in 1965, there was a lot of progress made on various ideas about collapses. And in particular, Oppenheimer and Snyder calculated the collapse of a spherical cloud of matter. And they found that the star tends to close itself off from any communication with the distant observer. And only its gravitational field persists. So once the field collapses, then the star can no longer be seen. And people said that it was okay because you did a spherically symmetric simulation. Suppose you take a non-spherical object and it collapses. Can it lead to a singularity? And there were claims and counterclaims at that point. And it turned out that Just a moment. I'm getting some disturbance. There's somebody working outside my office window. I'll try and stop that. Okay, sorry for the interruption. We have some construction work going on, and they usually do it over the weekends. In any case, so while this controversy was going on, there was also some interesting discoveries made. The quasars were found. These are essentially thought to be black hole candidates, which are shining because of matter falling on it. And they were discovered, and they found that they had a huge luminosity, about 10 times 40, 10 to the power 14 times the luminosity of the sun. And as I explained, the only way you can get very high efficiency of emission in terms of rest mass energy is by using a black hole. So many other such discoveries were found. People were fairly convinced that these are probably black holes. So there was immediately a question and an attention paid to how they formed, and therefore Wheeler, who's one of the great physicists of the 20th century, started looking at this problem, and he discussed this with Penrose. So Penrose then came up with this singularity theorem, which is sort of an explanation for the collapse. So what he assumed was that there was a non-negative definiteness in the Einstein's energy expression, and so it comprises of if the singularities are not permitted to occur, that is, if it doesn't collapse to a singularity, then there are four possible reasons. One is that there's a negative local energy, the Einstein's equations are violated, the space-time is incomplete, or the quantum phenomena breaks down the space-time concept. And so he gave a topological proof of it. He took an initial spherical collapse, and then the exterior observer will see the whole event up to r equal to 2m, as was predicted by Oppenheimer and Schneider, and they don't see the singularity at r equal to 0. But after the matter crosses at r equal to 2m, a space-like sphere can be found in an empty region surrounding the matter. And this concept of a trapped surface, which is closed, is introduced. And this trapped surface, when the null geodesics, that is the light rays, meet it orthogonally, they converge locally in future directions at T2, right? I will explain this in a figure shortly. So the trapped surfaces will exist if the matter region has no sharp boundary, and even if spherical symmetry is dropped, provided that the deviation from the above situation is not too great. So even spinning black holes have the same property of having trap surfaces, and the argument is made to show that the existence of a trap surface, irrespective of symmetry, implies that singularity is necessarily developed. The proof is highly mathematical, involves topological concepts like Cauchy hyperspace, etc., which I won't go into in this talk. But this is essentially the idea. There's a schematic diagram showing the interior of the black hole. So if you have a space, because of the metric changing sign, there's 1 minus 2m by r. So at r equal to 2m, it changes sign. So the space becomes time-like, and you just the star falls into a singularity where the time stops, right? So this is the basic idea, and you can see that there's a trapped surface now shown in this figure, where once the matter enters into the trapped surface, all the uh, space vectors turn into time, and they just get into the time coordinate and into the singularity. And you can also see that the light cones are pointing inwards, and none of the photons can actually exit. Once they enter in such a way that they simply cannot uh, send any signals out. This is a diagram which was invented to solve such collapse problems, called the Penrose diagram. So when you transform the metric, you can transform it into an infinite future, infinite past, and you can. This is a finite size diagram. Even though the space is infinite, using an arctan function, you're able to do this, and therefore you're able to transform all this into a compact diagram and discuss the whole collapse in this very nice simple diagram. So here you have a singularity at the top where the time stops. So this is the time axis on the left with along the y direction, and you have the horizon which is marked in red, and then you have the infinite future and infinite past. So in this diagram, the light rays are traveling in 45-degree directions, right? So the you can see that the matter is entering in the surface of the star as enters the horizon at different points. So, what are the implications of Penrose's result? It is considered one of the greatest achievements since Einstein introduced general relativity into the theoretical physics landscape. And it proves that gravitational collapse cannot be stopped after a trap surface is formed. So, and it's easy to get the matter into the trap surface, because if you take a very massive black hole, the density of that black hole is uh, is of a 10 to the 8 solar mass black hole is just the density of water. So, because the density goes as 1 over m squared, so the larger the mass, the density will be smaller. So after this, Penrose, along with Stephen Hawking, went to show that similar results also apply to the cosmological singularities. This is the Big Bang. So there it's a time reverse situation. So we are actually inside a singularity in which the whole world, universe began with a bang from a single point, and we are a part of that point. And of course, there's quantum fluctuations and inflation, which is thought to explain how the expansion occurred at the early time. So there's a very nice discussion in 1969 by Penrose, who wrote a beautiful summary of many of these results. And in a review article, Senovilla and Garfinkel, they provide a thorough description of the theorem and its historical background. So Penrose's discovery triggered a new era in physics and astronomy. The strange dark objects that Michel and Laplace speculated about were deeply rooted in our modern picture of gravity. It was after Penrose's discovery that black hole finally stuck as the name for this exotic gravitational anomaly. And the American physicist Robert Dicke was the first to use this term during lectures in Princeton in 1960, and Wheeler also made this very popular. There are more modern trends. Recently, there's a proof that the trap surfaces can be even formed without matter. And Ed Witten, 1982, and Schoen and Yao proved the positive energy or mass theorem. And in fact, Witten and Yao got the Fields Medal, which is the highest prize in mathematics for this proof, at least for the part of this proof. Partly for this proof, rather. And recently, there's a paper by Chesler, Narayan, and Curiel, who find singularities in a collapse around a Reisner-Nordstrom black hole, which is actually a black hole with charge but no angular moment. Here's a cartoon, which is the famous cartoon where the naked singularity is trying to cover itself with a fig leaf, and there's a cosmic censor, who drops the fig leaf. So this is sort of a parody on the situation. Cosmic censorship has always been under attack. It's not, there are several. It's a controversial topic. Nevertheless, it has now been recognized as, a, a dominant explanation for the gravitational collapse and formation of black holes. So, subsequent to this idea by Penrose, supermassive black holes have been found in many galaxies, in centers of many galaxies through direct observations, and there was a disk of matter which was found. So you measure the velocity of the particles in the disk, you're able to infer the mass, and you're also you're able to infer that the mass exists within a certain radius. In the case of MAD7, it was found to exist within, 30,000 Schwarzschild radius. So the question was, could it be a dense cluster of stars? So in another system, in NGC 4258, they found out using H2O maser that the, the compact system is 0.13 parsec, and 1 parsec is, by the way, 3 light years. And uh, again, this meant that you would have a very high density of matter, 10 to the power of 9 solar masses in per parsec cubed. So if you put this much of mass, it's very unstable and it would collapse. So it has to be a black hole at any rate. So the next part of the discovery, next part of the prize, next half of the prize went to, as I said, Genzel and Ghez, and they discovered the black hole at the center of our galaxy. So this is the Milky Way, this is the solar system, and you can see that 26,000 light years away, we are sitting at 26,000 light years away from Sagittarius A, which is where the black hole is located. And if you divide by 3, you can get the answer. So if it's 26 by 3, so this is 1,000 into 1,000. So 26 by 3 is roughly 9. So we are about 8.5 parsecs away from the center. 8.5 kiloparsecs, pardon me. So what was the essence of the discovery? So they found several stars which are going around the black hole. So once you find map the stellar object orbits, you sort of measure the points on the sky of these orbits, measure the radial velocities, then you're able to construct the orbits of these stars which are seen in this in the diagram on the left. Top left, you see several stars, S1, S2. So these are the stars which have been marked out, right? And Sagittarius A is marked here, so you can see the star go very close to the black hole. How was this done? So there's a mass concentration which was found at the center, and the typical speeds of the stars is 1 over square root of r, just like Newtonian mechanics. And with a spatially distributed mass, there were two observational teams, one led by Genzel and one led by Ghez at University of California. They were monitoring motions of stars using in the galactic center for decades, because the star itself takes about one of the stars takes about 18 years to go around the around the black hole. But one of the problems with this was that there's a lot of obscuration due to dust, in the interstellar dust. So they had to operate at wavelengths of 2.2 centimeters. And that is when the attenuation was reduced by a factor of 10. The other point was, because you have to take long measurements to get enough signal, you can only do it on the ground and not in the sky. I mean, not in a space-based instrument. So there's a technique which was initially used called the speckle interferometry. So what you do is you take snapshots, 0.13 seconds. You take snapshots, and then because of the turbulence in the atmosphere, these snapshots are slightly shifted. So what you do is you shift and add them. So once you shift and add them, you get a signal, which is a better, strong signal of the sky. So once you get the points marked out, you can actually measure them. Their positions and the velocities are also measured in the sky. So after having done these proper motions studies, you can actually find a stellar dispersion. That is, a velocity is a function of radius from the center where the black hole is located. And then you get this very familiar 1 over square root of r. So this is a result from Eckert and Genzel in 1997. After this, a new technique came into play, called the era of entry of adaptive optics. So what is adaptive optics? So suppose you have turbulence in the atmosphere. What you do is you have a laser, you shoot a laser into the top, and then there is a source that is created. So it's called laser guide star. So this once you light up a part of the atmosphere, usually some sodium laser or something is used, and that light, when it enters the atmosphere, because of turbulence, there is a sort of a distorted light, and through the telescope you'll see a distorted wavefront. So once you measure this distorted wavefront, you correct that in a deformed mirror. So the mirror can be deformed, and with the correction you get a straight wavefront. So when you're measuring the star, you'll get the same distortion, but that distortion is corrected by changing the surface of the mirror, shape of the mirror, and so that's what you then you get a straight wavefront, and this is called the adaptive optics technique, which is done real time. One of the interesting stars which are orbiting the black hole was S2 star, and whose orbit was measured for 26 years, right? And this is nearly 3 decades. And you can see that careful measurements were done. This is, a large part of it was done using the adaptive optics technique. And you get a very neat elliptical orbit. This is the radial velocity measurements. This is the velocity towards the observer. As you can see, there's a fluctuation because it's goes fast when it goes near the pericenter of the orbit, and this is the blow up of the orbit very close to the pericenter. So recently, a student of mine, Prerna Rana, and we did a calculation of orbits around black holes, and we solved the integral of the orbits using Hamiltonian mechanics in Kerr space-time, and we published this last year in Classical Quantum Gravity. So this gives you a very analytic expression for the orbits in a different coordinates, in a different parameter system, using eccentricity and inverse lattice rectum, which is the inverse sum of, it's the harmonic mean of the pericenter and apocenter of the orbit, the spin of the black hole, and something known as the Carter's constant. So these are very useful formulae, which is otherwise, numerical integrations are tough, and the other formulae were very more complicated. So we found this very interesting formulae. So now you can actually solve for it. For example, if you have the time and the phi, which is the azimuthal angle, you can actually integrate out, and once the integrations are done, you get this expression, and these expressions are essentially functions of elliptic integrals. So all you need to know is E and the mu, which is the as I said, the inverse lattice rectum. So you solve for this, and then you're able to find the spin and the Carter's constant by using two equations. So E and mu comes from observations. Alpha is just the phase of the orbit. So you can also find fundamental frequencies of bound orbits. And these are some of the orbits that you can generate using the formulae. You can see sort of a chaotic orbit and a spherical kind of an orbit. Axisymmetric systems. You can also get funny orbits like this, which sort of enter and then do several circulations around the black hole. And then the standard rosette pattern, which is also seen as. So what really happens? You have this rosette pattern which is happening on the left, and the other thing that also happens is the orbital plane itself goes up and down, right? So there's an oscillation of the orbital plane. So both these things happen. It's called the relativistic precession. So if you take the S2 star orbiting the Sagittarius A, it has got a delta phi of 12 minutes. The eccentricity is 0.88. The RP is 120 AU. So you put all this in our calculation. This is how the simulation looks. You solve for this delta phi and TR, and you put that in the equation, and you actually calculate the spin and Q. So having done this, so this kind of thing can be done for many systems, and provided you have very accurate information. Another important question which was raised by one of the Nobel laureates herself was why don't you see matter falling onto the black hole? And to address this question, actually I was involved in two papers with a former student of mine, Mageshwaran, and with a current student, Dipanvita, where we did both non-relativistic and relativistic calculations of how many stars can actually be trapped or can fall into the black hole. And it turns out to be one in a million, 1 in a million years. So that's how slow it is. Now there's a new mission called the 30-meter telescope. I don't want to get into the details of this, but this being a large telescope, you will be able to explore black holes in much more detail. You can explore the full range of 10 to the power 6 to 10 power 10 black holes. You can explore the relationship between the black hole and the bulge. That's the bulge of stars which are there in the central parts of the galaxy. So all this is going to be exciting times once the black hole, once the TMT is set up, which can be in the future, say about 5 years from now. There are many Indian scientists who have contributed to the study of black hole science, and one was Chandrasekhar, who got the Nobel Prize and for the prediction of the existence of black hole. A.K. Rai Chaudhary, who was a teacher for a long time at University of Calcutta, Presidency College, and he was involved in finding the Rai Chaudhary equation, which is an important ingredient in the proofs for the singularity theorems of Penrose and Hawking. And C.V. Vishweshwara was another scientist who found oscillatory solutions to the black hole, and it's one of the important reasons for the discovery of the gravitational waves that was done in 2017. I mean, that was done in 2017. Discovered in 2016, the prize came in 2017. So this is more or less what I want to say. Penrose's discovery of the singularity theorem has been a boon for astrophysics and black holes research, and more than a half a century since that has passed, and since that conceptual breakthrough and technological advances have enabled probing closer and closer to the black hole event horizon. The observations by LIGO, which was awarded the prize in 2017, the exquisite observations by Genzel and Ghez, sharing this year's prize, as well as a remarkable picture of the center of M87 taken by the Event Horizon Telescope, are all compatible with the existence of supermassive black holes. The extent to which the structure of black holes surrounded by an event horizon is actually match the predictions of GR is still an open question. And of course, the nature may have something in store for us later. Thank you very much. I will just end with this cartoon. This is done by Vishu, but in my imagination, this is one of the persons who discovered gravity, one of our Indian ancients who discovered gravity, but he didn't live to tell the tale because he was sitting under a coconut tree. Thank you very much.
Thank you, sir. That was a very wonderful talk. We are having some questions from audience to you.
Okay, sure.
Himanshu will ask.
Yeah, hello. Good morning, everyone. So there are some questions from YouTube Live. So Rosalind Behra asks how time gets slower near the black hole.
Okay, I think I showed you that. If you look at the metric, you see this d tau squared equal to 1 minus 2m by r dt squared, right?
Yes.
So if you take r very far away, then you get dt squared. But if you take r very small, r, let us say, uh, so what happens when the d tau is a conserved quantity? So when you divide by 1 minus 2m by r, the dt at r and the dt at infinity, you can see that the time uh, difference will uh, will be ticking faster than the local clock. So that's what happens.
Okay, sir. So also you talked about that adaptive optics and
Hmm.
how those mirror change to counter for the turbulence in the atmosphere. So
Hmm.
how those mirror actually counter for this turbulence in atmosphere? Are those like segmented mirror that change their angles or?
Correct, correct. So you are actually doing a deformation at the
Hmm.
mirror level to correct for the waveform, and therefore you're able to correct the wavefront, right? So here's the picture which I showed you earlier.
Yes.
So because you have a distorted wavefront, you can actually see that on the right hand side you can see a distorted mirror. So
Yes.
that correct for this, it will be sort of the opposite sense uh, and of the distortion, and it
Hmm.
will give you a straight image.
Yes, sir. So, Shritik Mishra asks, could black holes be used as an energy source?
Yeah, precisely. I mean, you mean on Earth or something?
No, if in future maybe some we humans become intergalactic species, so can it be harnessed as a energy source or anything like that?
Well, yeah, since black holes can come in various sizes, you can make baby black holes. But I think that is a very interesting suggestion. But I don't think it's feasible, at least from the modern. There is nothing that is known that can do it as of now.
Okay, sir. And another question, well, what happens to matter and light once they enter the event horizon?
Yeah, as I said in the first picture, which was of the collapse, which I showed you, uh, matter collapses and the light cones are pointing inside. You cannot see, even light cannot escape. So you will not be able to see anything coming out, right? So that is the concept of an event horizon.
So, could you tell us more about the light cones?
So you can see the light cone here. There's a future and the past, and the
Okay.
light cones are pointing inwards. That
Hmm.
means inside the event horizon. So you cannot see the light coming out. Since you have to be within the cone to observe it, and see the observers are outside, you cannot see it.
Okay, so the dotted part is the past of the light cone.
Yes,
Okay. So once it enters, so the dotted parts, the light only goes inside. So the observer outside cannot see it.
correct.
Sure, sure. Okay. And yeah, that's the questions. Another question, sorry. Yeah, my question that how do we know the age of the universe from expansion of it? So how are we so sure that it expands
Well,
from?
it's about 13 billion years, and I think it's like 1 over h naught. And the
Mm,
Hubble 1 over the expansion rate, roughly. You can do it for different cosmologies, but it's about 13 billion years is the current value.
okay. So if others have some question, they can please ask. Yes, there are some more questions in the chat. So, Aman asks, sorry, asks, So during a black hole collision, why do their orbits decay instead of revolving each other forever in a loop?
Because there's gravitational radiation. So once the once you're in revolving around the black hole, it's like for example electromagnetic radiation of two charged particles, right? So the since you're going around in an electromagnetic field, you're radiating away the energy, right? So that is the same thing which happens in a gravitational collapse when there are two uh, objects sort of orbiting around each other. The gravitational field is being radiated away.
Okay. One more question is there. Why don't the nuclear forces increase as at the same rate as the gravitational forces?
Well, you can't certainly demand that they increase. Whatever it is, and it sort of cannot stop gravity. See, the gravity eventually is the overwhelming force in the universe. It acts at largest. See, the nuclear forces, etc., have ranges. They cut off. The nuclear forces cut off within the scale of the nuclei, and if you have charges which are canceling out, even the electromagnetic forces get cut off. So the only long-range force in the universe is gravity.
Sure.
So if there are no more questions, Vinil will be giving a vote of thanks.
Yeah, Deepika, thank you. It's now my honor to propose the vote of thanks on behalf of Indian Institute of Information Technology, Design and Manufacturing, Kurnool, and myself. I express my sincere gratitude to Dr. Arun Mangalam, our chief guest, for taking time out of his busy schedule to give his talk. I thank Murli sir for giving us this opportunity to host this webinar. I think I can safely say we all learned a lot today. Thank you, sir.
Welcome and best wishes to your institute and your astronomy club. Bye bye.
Thank you so very much.